What kind of data? Last. Exam number 3. Multiple what? Something or other, yes! Most annoying sound in the world, what? My voice at 8 a.m. 3 tests, that's it, 3 tests. Give me one of them. Good, what kind? How many data sets? 2, exactly. You've got 2 independent samples of a t-test. Actually, you know what, look around to this. 2 independent samples actually is for 2 of the 3 tests that I can give you on your exam on, when's your exam?
Next Thursday.
Thursday.
12.
There we go, Thursday.
Oh, yeah.
Thursday.
No.
Thursday at 12.
No, it's gotta be 10 to 12. No, it's gotta be 8 to 10. 8 to 10.
8 to 10.
It's gotta be 8 to 10 because it has to coincide with your class. 2 independent samples. So I heard a t-test. Yes, that's one of them. If you're testing 2 means, that's going to be a t-test. If you're testing 2 means. What else can you test besides 2 means? Yeah.
So we're not going to do any single parameter on the
No, you did it on the last exam.
We did it.
No need to do it again.
So
I assume.
2 property.
And then, good! And then the other one is when you have 2 proportions. Yeah. So that's a z-test. Or 2-prop z-test.
So isn't the other one a 2 sample?
It's called a 2-sample. Yep, 2-sample t-test. Exactly. There you go. That's that. Then what's the last one?
Goodness of fit.
That's it. That's it. Is you're good as a fit test. And why do you need that?
So we're not doing ANOVA?
Nah. I mean, I could teach it today. That's dumb. Just to teach it for a test is stupid. But why? Let's come back to that real quickly, though, because I want to mention it to parallel off of this, but not on the exam on Thursday. Why do you need this?
Multinomial.
Right. Thank you. Thank you, Will. Yes, over here, you've got a nice test for 2 proportions. As soon as it goes above 2, you run into a problem. As soon as it goes above 2, you start losing confidence by running these paired off, 2 at a time. So this is when you have those multinomials, which means you're going to have multinomial. You're going to have P1, P2, P3, maybe up to more. It could stop at just 3. The data sets I'm looking at probably don't have any more than 10, because after that it just gets tedious for you guys to set the data up. And that's your your golf program. Go ahead, Rosie.
With the golf on the test, instead of asking us to give a concise sentence explaining the conclusion, are you going to do a Pierce does not?
It's going to be a Pierce does not. Yeah, I know. I didn't. It's one of those things where
I think that confuses you.
I know.
When you're thinking
I know it does.
more
And that's what I thought about this term. Thank you for saying that. I appreciate that. This term, I realized what I used to do in 244. I've done it for the past like 3 or 4 years. Is I'd start with the block template, which you saw in your couple homeworks, and then disappear. And I went to the quizzes looking like, write the test statistic, write the p-value, give me a clear, concise conclusion. And I thought I was weaning you guys, and this not just you guys, but the previous 244s, I'm weaning you off the template. And then I realized in 10 weeks, I shouldn't be weaning after 2 weeks. I should stay that way almost the entire time. The problem is getting that back in there and fixing all the templatizing was sluggish this time around. But yes, you're going to have all the templates just like on that last exam, on this exam. So you'll still identify error, but you still won't have to calculate any probabilities of error. Just so you realize what they could possibly be. Yeah?
With goodness fit, your p-value is small.
Still means you believe the research hypothesis.
Okay.
Yeah,
So
p-values mean the same thing,
yeah.
and that's the beautiful part. Has anybody got a chance to look at the take-home exam yet with the Excel spreadsheet? You're going to have a p-value on that bad boy too, and it means the same thing. If it comes in under 5%, something, as Danny said, yep, something changed. If it comes in under 5%, something changed. Now the something is what the hypotheses spell out for you. That's why it's important to write them first, so you know. And that's something else I realized too. After a while in 244 in the past, I stopped having students write hypotheses. That's stupid. You need to keep writing them so you understand what you're testing. I mean, in my mind, the students had them in their head. Like, oh, they know what they're doing. I'm like, wait a minute, after 2 weeks? It might be a stretch a little bit.
Doing that quiz just now, like it's just slightly more confusing.
It is, I know, and I am hearing you totally, and it's a matter of, what it is mostly is not being a trained statistician, but knowing what you guys need to know. And when I write them like that, I leave too much off of what you need to demonstrate that you know. I think you know it, but writing it down just reinforces that. So that's why I set these up like that.
I almost did it on my own. Also. It's like, I'm
That's
just
okay.
thinking myself.
That's okay. You'll have the opportunity on here. Now Rosie mentioned one that I won't have on the in class, which is an ANOVA. I'm going to put it over here in orange. And like I said, I could easily go through it today, which is dumb to do, because I would just teach you how to plug numbers into a machine without analyzing it. Because it would take us literally probably 2 days to go through the computations of an ANOVA. That's when I realized on Tuesday, I'm like, we'll leave it off. But just so you know, you use an ANOVA, and you'll probably end up seeing this in your careers at some point. This is the average version of a goodness of fit test. So the reason we have goodness of fits is because you have too many proportions to test this way. So 3 or more proportions. And ANOVA allows you to test 3 or more means. And the only reason I'm bringing this up is you're going to see it someday. And if you take a stat class at OSU Cascades, they'll make you do these things by hand. And the ANOVA will take you literally a day and a half to crush through the computations for, which is fine. I mean, it's actually good to see it once. You see what the hell's going on. You see why it's called ANOVA and not ANOMU. And that'll make sense if you actually sit down and do one. You'll probably end up seeing the results of one of them in a journal somewhere. For example, I was doing some research on ADHD medications. Adderall, Ritalin, different dosages. And we're trying to see if different dosages of different ADHD drugs result in different cognitive performance on tests. So there was a control group. A bunch of ADHD kids were given just a placebo. And then some kids were given 15 milligrams per kilogram. Was it milligrams per kilogram? No, just milligrams. 15 milligrams of Adderall, 30 milligrams of Adderall, 15 milligrams of Ritalin, 30 milligrams of Ritalin, and there was 15 and 30 of something else too, which I can't remember now. So you had 7 different groups to test. Well, that's the problem. You can't do this. Because if you do this, you're testing 21 different pairings with 7 groups. That's ludicrous. You're 95% to the 21st power of confidence, which is essentially 0 at that point. So ANOVA lets you test them all at the same time. The computation is a bit tricky though. And that's you'll work through it at some point. I mention it only because, number one, you're going to see it, and I did make a mention of it on your out-of-class exam. The very last question of your out-of-class exam makes you guys go online and look up other ways to test the same tests we did in class, non-parametrically. And again, because we only have 10 weeks together, I'm not going to make you learn them all. That's dumb. If you understand what a p-value is, which it sounds like you guys do, yay, I'm stoked. You walk out of this class, you can read a journal and understand what it's saying, you can learn a new test, get the results back, and like you just said, Rosie, a small p-value means the same thing? Yes, always. So I'm going to have you guys, on your out-of-class exam, identify each of these tests, what we did in class, and then also go online and find some non-parametric test that does the same thing without making the assumptions the parametric test does. And I gave you some examples so you can see what I'm talking about in there. So you have to find one for the ANOVA, but that's not hard to do because they're used all the time. So just get in there and Google away. Cool? Yeah. So that's it. I'm thinking maybe 2 of each with the templates. That way, one of each seems a little too short. Like it just seems like the 2 of each will occupy an hour of time, and you'll knock it right out. There. That's it. That's it. Just 2 each of those tests. It won't take you 2 hours. I mean, you'll have the whole 2 hours, of course, if you want them on Thursday, but you probably won't need them. Your biggest job is really going to be looking at the exam and going through the data sets and realizing which one's which. Like, oh, this is a GOF. Oh, this is 2 proportions. Oh, this is this. Oh, this is that. And there's certain things you can look for. Right? There's certain things you can look for. What's a good clue? You're looking at a goodness of fit test. What's a good clue? Think about the ones we did in class. You're going to have more than 2 data sets. Right? Look for 3 and 4 and 5 and 6 and 7 data sets. As soon as you see that, you know it can't be anything else. It's going to have to be goodness of fit. That's that. Beautiful. Or a data set broken up more than 2 ways. We can say it a couple different ways because you can view like the M&M experiment as one large data set of M&Ms broken up into 6 categories, which is essentially the same thing as saying there's 6 data sets. Okay? So I think we can identify a GOF pretty easily. How can you differentiate between these guys?
Average or proportion.
Exactly. You did it on your last exam. I gave you guys the hypothesis test on your last exam, and you had to differentiate. One was a proportion test and one was an average test. And you realize that, oh, if I'm measuring something, it's going to be an average. If I'm measuring something, it'll be an average. If I'm doing a percentage of something or something out of something, it's going to be proportions. There's that. So, the skill you need to differentiate these two is you already have from your previous assessment, and then all you got to do is make sure you tack that on. And just make sure you know where all these things are. You got a programming GOF, and you've got these two tests in your test menu. Yeah, Rosie.
Do we always use data, right?
For
the key samples?
It depends on the data sets I find. That's a good question. I like to find ones where you have data. That's my personal favorite, because that way you can actually graph them and look and make sure they're bell-shaped. But sometimes when I'm reading journals, I only find summary statistics, in which case you go to stats. So it depends on what you get. If you get big, long lists of data, then yeah, go to data. But if I give you X bar, S, and the sample size,
okay,
then you have to use the stats. I try to find data.
but you will put it down like this is X bar. So
Oh, God, yeah. That's the indication. If you see that, oh, he's got statistics. I try to find raw data whenever possible. That's my favorite. So, there you go. It's the whole shebang. I was hoping this was going to be the term I was going to get the power bracelet data from that one researcher I told you about, the one where he tested power bracelets the right way. But he's still sitting on it. So, I don't know. I'll keep tickling. Cool. That's it. What questions you guys have? How was the last project? Woo! A lot of butterfly yesterday. Drank a lot of pool. How was the last project? Excel? Decent? Yeah? Decent? Good. I like doing it that way. Did you guys catch that you were actually doing a hypothesis test? Did you catch? You weren't in the traditional sense of one of these, but did you see how that really was a hypothesis test? By one of the cells. It was a command I made up. I had to create the command. But what was the one question that was asked in every single data set? Is the data
increasing or decreasing?
before that? Because if you said if it's increasing or decreasing, you already decided that the data was what? Linear. That was the question when I said, is the data linear enough? That was essentially doing the same thing a p-value does. Because if you say no, that means you've got a big p-value. There's no reason to think the data is linear. But if you've got a small p, now I hid the p-value from you because nobody actually calls them p-values with linear regression. That's why I pulled this out of the book. Because your book, like every other stat book, treats linear regression as a t-test. Why? I don't know. Nobody in the world actually does that. They use what's called the R value, the correlation coefficient, which we talked about in the project. That's what they use. And the closer those things get to the absolute value of 1, the better the fit to data, to the linear data is. So that's what I set it up to act like a hypothesis test, but not be a hypothesis test. So, and then your job, of course, the best part about that, my favorite part about that project, you had to decide visually which ones looked like lines. Yeah. Which ones of those actually kind of appeared to be linear. The second pass filter of the computer, that just makes sure that if you said it needed to be a line, okay, if you believe it's a line, I trust you. Now, is it liney enough? And some of those probably didn't look like lines, it's just like scattershot, which it should have been. And there was one intentionally I did that wasn't a line at all because it ended up being an algebraic connection. But I like some of the data sets, the Rate by Professor, popularity versus easiness rating. That was just fun stuff. There was no relationship there, was there? That's the one that it was just scattershot. Yeah, it's interesting too because I put that on almost as a joke. But then I got a COCC internal memo that went up on a printer that said somebody actually was correlating Facebook likes with school population and taking it seriously. Like they were actually looking at the size of the community colleges in Oregon and the number of Facebook likes the Facebook pages had, and they were correlating them and ranking them. I'm like, wow, that's completely pointless. I mean, it's adorable. It's a way to do statistics, but it's like the most meaningless statistics I can think of. But that's the thing. That's the thing. You can then throw it up on a correlation and be like, yep, there you go. Nothing. So there's a way to quantify the silliness of it. You know. I'm not saying that looking at school numbers population-wise is unimportant, nor am I saying looking at Facebook likes is unimportant, maybe. But I'm not sure that correlating them tells you anything that a Ouija board couldn't. So anyway, it was a little twist on your previous projects, definitely Excel based. And you come late the scatter plots. Did the video help? If you guys had a chance to watch it, I don't know if you got
Very helpful.
It's gone into Excel 2013. I think that's the new version of Excel. But just having I think when I incorporate more of those videos in the projects from now on, I think the technology will help for sure. What questions you guys have? That was the project, that was the last quiz. What do you got? What do you got? Anything you got? I should log on.
I'd like to see it
Can we do some practice?
to proportion to Prop C example.
Let's do one.
Yeah, can we do a couple examples of each of them?
Find me one.
Well, that might be-
Well, let me log on. Let me log on here. You can make one up right now. Small data set here.
Oh, that didn't, the project doesn't have to.
You know what? Let's make one up while we're at the computer world. Let's make one up for you, Will. We're going to test the proportion. Well, actually, get left-handers in the room first of all. This might be hard with the small one now. Shit, it's not going to work.
Where the plots are.
What the fuck can we do? Okay, I know how we can do it.
Increasing and eliminating.
Any of you drive more than 5 miles to get here today? More than 5 miles? Okay, that's something we can test. So what we're going to test is two proportions. We're going to see is the percentage of males driving. I'm going to switch the camera over here. This is a good question. I was going to test left-handedness, but it's hard to test it when nobody's left-handed. Is the percentage of males driving more than 5 miles to COCC? Let's just say different, because I didn't actually count how many there were. Different than that of females. Now we got a ridiculously small data set, so it's a little bit fictitious in that respect, but whatever, totally fine. So let's it doesn't matter how we label them because we're just doing it different, but we'll just call P1 the percentage of males driving more than 5 miles,
Yeah.
and we'll do P2 be the percentage of females driving more than 5 miles. So the first thing you're going to have to do is identify the data, and I'll have this all clocked out. Actually, this is similar to the one to quiz from last week. Quiz from last week is a percentage of, I think this was the quiz from last week, percentage of males in my classes different than the percentage of males in COC overall. So it's the same kind of thing, except we're checking both genders here. So as far as the guys, I'm going to go X1, N1. Now I know what N1 is. Actually, I don't. I can find out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N1 is 10. How many guys drive more than 5 miles to get here? We got 3. 30%. All right. So it's somewhere in a problem. I'll state that, you know, in this blah 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 class of size blah blah how to drive more than 5 miles, or whatever we're measuring. Okay. Now let's check the females, of which we have 2, 3, 4, 5, 6, 7, 8, 9. We got 9 of those girls, excuse me. And how many drive more than 5 miles? Ladies? 1, 2, 3, 4, 5. Ha-ha! Sure as hell looks like it. Sure as hell looks like it with that data. So we can make it one tail, but the hell, leave it two tail. Looks like there's a higher percentage of females than males. But with a sample size that tiny, there might be such a margin of error on it that it's meaningless anyway. I don't know. That's kind of the beauty of the test. It takes care of the measurement of 44% versus 30%. Yeah? Right? Not 44%. 55% versus 30%, which is a 25 percentage point increase. But if the margin of error is any more than, say, 10 or 11 or 12%, that's a meaningless increase. And that's what the test measures out for, is it actually draws an interval around it. So let's do it. Your hypotheses, and you'll have these this space left for you on the exam, are going to be what? What's the null hypothesis going to be in this case?
It's not different.
That it's not different. That it's the same. Exactly. That it's the same. There's no difference. If you're looking for a difference, you're going to go in assuming there isn't a difference and try to see if you can knock that out of orbit. That's the whole idea every single time. If you're trying to show that something weird happened, you have to define something weird as the opposite of what normally happens. And you're not going to go in assuming there's a difference. You're going to go in assuming there's no difference and try to knock it out of that curve. And the opposite of that exactly is that they're not the same. I don't know why I put that backwards. Apologies. Cool? All right, let me get the machinery out. Don't have to crank these by hand. Thank goodness. Shut this down and shut it back up again.